What if I told you that just 5 degrees could rewrite the entire story of our planet? Not 5 degrees in your living room, not 5 degrees between a chilly morning and a warm afternoon, but 5 degrees across the entire Earth. It sounds almost trivial, doesn't it? The kind of temperature difference you might not even notice when stepping outside. But here's the thing that'll keep you up at night thinking. Those 5 degrees have the power to transform ice sheets into oceans, deserts into rainforests, and entire continents into something completely unrecognizable. Tonight, we're diving deep into one of the most fascinating and frankly unsettling chapters in Earth's climate history. We're going back roughly 56 million years to witness what happened the last time our planet experienced a global temperature rise of just 5 degrees Celsius. And trust me, what unfolded during that period will completely change how you think about climate, about change, and about the delicate balance that keeps our world habitable. Before we begin this journey through deep time, I'd love to know where you're watching from and what the temperature feels like in your corner of the world right now. Are you somewhere cold, where the idea of warmth sounds appealing? Or maybe you're in a place where the heat already feels overwhelming? Drop a comment and let me know, because in a strange way, whatever temperature you're experiencing right now is part of this much larger story we're about to explore. If you find yourself drawn into these kinds of deep explorations of our planet's history, I'd really appreciate it if you could hit that like button. It helps more people discover these stories about our remarkable Earth. And if you're the type who loves learning about the bigger picture, about how our world really works, consider subscribing, because we've got so much more to uncover together. Now, let me paint you a picture of what 5 degrees of global warming actually means. When scientists talk about global average temperature, they're not talking about the reading on your local weather app. They're talking about the mathematical average of temperatures across every square inch of our planet, from the scorching equatorial deserts to the frozen Antarctic wastes, from the depths of ocean trenches to the peaks of mountain ranges. It's a number that represents the entire thermal state of Earth's climate system. Here's what makes this so remarkable. Throughout human civilization, global average temperature has fluctuated by maybe 1 or 2 degrees at most. The difference between the medieval warm period and the Little Ice Age, events that dramatically shaped human history, was less than a single degree. So when we talk about 5 degrees of global warming, we're talking about something that dwarfs anything our species has ever experienced. But Earth has been there before. About 56 million years ago, during an event that scientists now call the Paleocene-Eocene thermal maximum, our planet underwent exactly this kind of transformation. The world heated up by approximately 5 to 8 degrees Celsius in what, geologically speaking, was the blink of an eye. And what happened next was nothing short of extraordinary. Picture this. The Arctic Ocean, that frozen wasteland at the top of our world, was warm enough for palm trees to grow along its shores. Not metaphorically warm, but literally tropical. Crocodiles basked in rivers that flowed where today we find nothing but permafrost and ice. The Antarctic, that vast white continent we think of as permanently frozen, was covered in lush temperate forests. There wasn't a single ice sheet anywhere on the planet. The oceans themselves became something almost alien compared to what we know today. Sea levels rose by more than 50 meters, story building. Roughly the height of 15 entire continental shelves disappeared underwater. The coastlines of North America, Europe and Asia were drawn in completely different places. What we now call the interior of continents were shallow, warm seas teeming with life forms that had never existed before and would never exist again. But here's where it gets really interesting. This wasn't some gradual, gentle warming spread out over millions of years. The initial trigger happened fast, probably within just a few thousand years. Massive amounts of carbon dioxide and methane flooded into the atmosphere, thickening the air and trapping heat with an efficiency that transformed the entire planet's energy balance. The source of all that carbon is still debated among scientists. Some evidence points to enormous volcanic eruptions that cooked carbon-rich sediments on the ocean floor. Others suggest that the warming itself triggered the release of frozen methane deposits, creating a runaway feedback loop that amplified the heat. Whatever the exact mechanism, the result was unmistakable. The atmosphere became a heat-trapping blanket, unlike anything Earth had experienced in tens of millions of years. Now, you might be thinking this sounds like a climate disaster, and in many ways, it was. The oceans became acidic as they absorbed massive amounts of carbon dioxide. Many marine species went extinct as their shells simply dissolved in the changed water chemistry. Deep ocean currents, those great conveyor belts that circulate nutrients and oxygen around the planet, slowed to a crawl or stopped entirely. Vast areas of the seafloor became oxygen-starved dead zones. But here's the part that's absolutely mind-bending. Life didn't just survive this transformation, it exploded into new forms of incredible diversity. This period of extreme heat became one of the most creative chapters in the story of evolution. The mammals that had been small, timid creatures during the age of dinosaurs suddenly found themselves in a world of unlimited opportunity. Forests spread across the globe like never before. From the equator to the poles, dense woodlands covered nearly every available piece of land. These weren't just any forests. They were lush, humid, tropical jungles filled with plants and animals that had never had the chance to evolve before. The warmth and high carbon dioxide levels created growing conditions so favorable that vegetation exploded in size and diversity. In these endless forests, early primates swung through canopies that stretched from what is now Wyoming to what is now Germany. Ancestors know. Tiny horse bigger than house cats, grazed in fern-covered meadows. The evolutionary ancestors of almost every major group of modern mammals appeared during this hothouse period. In a very real sense, the extreme warming didn't destroy life on Earth, life possible. Think it made modern about that for a moment. The mammals that would eventually give rise to elephants, whales, bats, and yes, eventually us, all trace their lineages back to this period of intense global warming. The heat that could have been catastrophic instead became the engine of innovation that created the biological foundation of our modern world. The weather during this time was unlike anything we can imagine today. With so much energy trapped in the atmosphere and oceans, storm systems became massive. Hurricanes that and persistent would dwarf anything in recorded human history swept across the expanded seas. Rainfall was torrential in some regions and completely absent in others. The hydrological cycle, the movement of water between ocean, atmosphere and land, was supercharged by all that extra heat. Yet despite the extreme conditions, ecosystems found ways to thrive. Plants evolved waxy leaves to handle the intense humidity. Animals developed new strategies for dealing with heat and unpredictable weather. Migration patterns emerged that spanned continents. The planet became a laboratory for adaptation and innovation on a scale that's hard to comprehend. What makes this ancient warming event so relevant to us today isn't just the temperature rise itself, but the speed at which it happened and the way Earth's systems responded. The Paleocene-Eocene carbon that entered the atmosphere during the thermal maximum came from multiple sources: volcanoes, methane deposits, possibly even the decomposition of organic matter as soils heated up. Sound familiar? The parallels to our current situation are both striking and sobering. Today, we're adding carbon to the atmosphere at rates that actually exceed what happened during that ancient warming event. The physics are the same. The chemistry is the same. The only difference is that we're compressing what took thousands of years into just a few centuries. But here's what the geological record shows us about recovery. The Earth didn't stay hot forever. Over hundreds of thousands of years, natural processes slowly pulled that excess carbon back out of the atmosphere. Rain weathered rocks, which absorbed carbon dioxide. The oceans gradually returned to normal chemistry. Ice began to form at the poles again. The planet found its way back to balance, though it was a different kind of balance than what came before. The species that survived the warming were forever changed by it. They carried the genetic memory of adaptation in their DNA. The flexibility and resilience that allowed life to flourish during that hot period became part of the evolutionary toolkit that would help life weather future changes. In a sense, that ancient warming event made the biosphere more robust, not more fragile. This isn't to say that rapid climate change is good or desirable. The extinctions that occurred during the Paleocene-Eocene thermal maximum were real and profound. Entire ecosystems disappeared. But what the fossil record shows us is something remarkable about the nature of life itself. Given enough time, life finds ways not just to survive change, but to use it as raw material for creating something new. As we continue exploring this incredible period in Earth's history, we'll discover how those polar forests actually grew and thrived, what it was like when crocodiles lived in the Arctic, and how the ocean currents that drive our modern climate completely reorganized themselves. We'll see how this ancient warming event offers both warnings and hope for understanding our own climate future. The story of what happened when Earth last heated by 5 degrees isn't just ancient history. It's a preview of the kind of planetary transformation that's possible when energy balance shifts. And as we'll discover, the lessons written in rocks and fossils from that distant time have everything to teach us about resilience, adaptation, and the extraordinary creativity of life in the face of change. So what did those polar forests actually look like? Imagine stepping into a world where the very concept of frozen wasteland doesn't exist, where the Arctic Circle hosts towering trees instead of endless ice. During the Paleocene-Eocene thermal maximum, the poles weren't just slightly warmer. They were completely transformed into something that would seem impossible to us today. At what we now call the North Pole, dawn redwoods stretched toward a sun that never truly set during summer months. These weren't stunted, struggling trees barely clinging to life in harsh conditions. These were massive, healthy forests with canopies thick enough to filter the humid twile, a green perpetual daylight into white at ground level. Birch trees, alders, and even subtropical species like bold cypress created an ecosystem so lush that if you could somehow transport yourself there, you'd think you'd landed in a swamp in Louisiana. Not the top of the world. The light itself was alien by our standards. During Arctic summer, the sun traced lazy circles around the sky, never dipping below the horizon. Plants had adapted to this endless daylight by photosynthesizing continuously, growing at rates that would seem almost supernatural today. Tree rings preserved in fossilized wood tell us these polar giants experienced growing seasons that lasted for months without interruption. No winter dormancy, no pause for cold, just constant, relentless growth fueled by warmth and 24-hour sunlight. But when winter came, it brought its own strange magic. Though temperatures rarely dropped below freezing, the sun would disappear entirely for months at a time. The forests would enter a kind of twilight hibernation, living off stored energy while waiting for the light to return. Animals had to adapt to this rhythm of endless day, followed by endless night. Some migrated south with the seasons. Others learned to slow their metabolisms during the dark months, conserving energy until the sun's return triggered another explosion of growth and activity. The Antarctic tells an even more remarkable story. Today's frozen desert was then a temperate wonderland of ferns, flowering plants, and shallow lakes. Fossil evidence shows us that even beech trees, the kind you might find in a modern temperate forest, grew within degrees of the South Pole. The continent wasn't covered by the massive ice sheet we know today. Instead, it was a green landmass surrounded by warm seas, supporting ecosystems that included everything from tiny mammals to crocodile-like reptiles. Think about what this means for ocean circulation. Today, the frigid waters around Antarctica drive much of the world's deep ocean currents. Cold, dense water sinks near the poles and flows along the ocean floor toward the equator, while warm surface water flows back toward the poles to replace it. This great conveyor belt of circulation helps distribute heat around the planet and brings oxygen to the deep sea. But when the poles were warm, this entire system worked completely differently. Without cold polar water to drive circulation, the oceans became more like giant lakes, with warm, stagnant layers sitting on top of deeper, oxygen-poor zones. This might sound like a recipe for disaster, and in some ways, it was. Many deep-sea creatures suffocated as oxygen levels plummeted, but the surface waters, supercharged with nutrients and warmth, became incredibly productive. Plankton bloomed in vast quantities, supporting marine food webs of extraordinary richness. The weather patterns of this hot Earth were equally extraordinary. With no temperature difference between poles and equator to drive air circulation, the atmospheric patterns we take for granted simply didn't exist. Instead of the jet streams and trade winds that organize our modern weather, the atmosphere moved in completely different ways. Some climate models suggest that massive thunderstorms might have dominated the tropics, towering higher into the atmosphere than anything we see today. Rainfall wasn't just heavier, it was distributed differently across the planet. The interiors of continents, which today are often dry because they're far from moisture-carrying ocean winds, received regular precipitation. What are now the great deserts of Central Asia and North America were lush, well-watered landscapes supporting forests and grasslands. The Sahara Desert didn't exist. Instead, that region was covered by lakes, rivers, and vegetation. But perhaps the most mind-bending aspect of this ancient greenhouse world was how it challenged our basic assumptions about habitability. We tend to think of extreme heat as hostile to life, but this period shows us something different. Yes, the warming caused extinctions and disrupted existing ecosystems, but it also created opportunities on a scale that's hard to imagine. The expansion of habitable environments from pole to pole meant that life could spread and diversify in ways that simply aren't possible in our modern, climate-zoned world. Consider the mammals that were evolving during this time. Without cold barriers limiting their movement, species could migrate freely between what are now completely separate continents. The ancestors of horses that evolved in North America could wander across land bridges to Asia and Europe. Early primates could spread from tropical regions into areas that today would be far too cold for them. This free movement of species created a kind of global genetic mixing that accelerated evolution and led to the rapid diversification we see in the fossil record. The plants were equally adventurous. Tropical species that today are confined to narrow bands around the equator could grow almost anywhere. Palm trees flourished in regions that now experience winter freezes. Mangroves spread along coastlines in temperate zones. The entire concept of climate zones, those neat bands of vegetation that we use to organize our understanding of global ecosystems, simply didn't apply. What's particularly fascinating is how this redistribution of life created entirely new types of ecosystems that don't exist anywhere on Earth today. Imagine tropical rainforests growing next to temperate, deciduous forests, with no sharp boundaries between them. Picture coastal swamps extending far inland, supporting mixtures of freshwater and saltwater species. These hybrid ecosystems, impossible in our modern climate, were the norm during the Paleocene-Eocene warming. The chemical changes in the atmosphere during this time were just as dramatic as the biological ones, with carbon dioxide levels reaching concentrations not seen before or since. Plants were essentially living in a world of unlimited fertilizer. The greenhouse effect wasn't just warming the planet, it was supercharging photosynthesis. Leaves grew larger to take advantage of the abundant carbon dioxide. Forests grew denser and taller. The entire planet turned greener as vegetation exploded in size and abundance. But this atmospheric chemistry had other effects too. The air itself was different, thicker with water vapor and greenhouse gases. Sunsets would have painted the sky in colors we don't see today. filtered through an atmosphere heavy with moisture and particles. The very act of breathing would have felt different, though not necessarily unpleasant. More humid, more dense, carrying the sense of abundant vegetation and active geology. This brings us to one of the most important lessons from this ancient warming. The changes weren't gradual and gentle. They were abrupt and intense. Within just a few thousand years, the entire character of the planet transformed. Ecosystems that had been stable for millions of years were suddenly thrust into completely new conditions. The speed of change meant that adaptation had to happen quickly or not at all. Some species couldn't keep up. The fossil record shows clear evidence of extinctions, particularly among creatures that were highly specialized for specific environmental conditions. But many other species not only survived, but thrived by becoming more generalized, more flexible, more capable of living in a variety of conditions. This evolutionary pressure toward adaptability created lineages that were better equipped to handle future environmental changes. The mammals that emerged from this period of intense warming were fundamentally different from their ancestors. They were more diverse in size, more varied in diet, more sophisticated in behavior. The evolutionary innovations that appeared during the Paleocene-Eocene thermal maximum, things like improved temperature regulation, more efficient digestive systems, and enhanced sensory capabilities, became the foundation for all subsequent mammalian evolution. As we dig deeper into this remarkable period, we'll explore how the oceans themselves became unrecognizable, how sea levels rose to heights that would redraw every map, and how life in the water adapted to chemistry that would be toxic to most modern marine creatures. We'll see how this ancient warming event offers a window into the kinds of changes that are possible when Earth's energy balance shifts dramatically. The story of those polar forests and the creatures that lived among them isn't just a curiosity from deep time. It's a demonstration of life's incredible capacity to not just survive change, but to use it as fuel for innovation and expansion. And as our own climate begins to shift in ways that echo this ancient warming, understanding what happened then becomes crucial for imagining what might happen next. The transformation of the oceans during this ancient greenhouse period was nothing short of revolutionary. While we've explored how the continents turned green and the poles became tropical paradises, the story beneath the waves is equally extraordinary and perhaps even more unsettling. The seas that covered our planet 56 million years ago would be almost unrecognizable to any marine creature alive today. Picture an ocean without a single ice cube floating anywhere on its surface. No glacial melt, no polar ice caps, no frozen coastlines. The water temperature at the North Pole was roughly the same as what you'd find in a modern subtropical bay. The thermal energy stored in these vast bodies of water was staggering, creating marine environments that operated by completely different rules than anything we understand today. But temperature was just the beginning of the ocean's metamorphosis. As massive amounts of carbon dioxide flooded into the atmosphere, much of it dissolved directly into seawater, fundamentally altering ocean chemistry. The seas became more acidic than they had been in tens of millions of years. For creatures that built shells or skeletons from calcium carbonate, this was catastrophic. Imagine trying to build a house while someone continuously pours acid on your construction materials. That's essentially what happened to countless marine species. Microscopic plankton, the foundation earing in of ocean food webs, began disappearing in massive numbers. Their delicate calcium carbonate shells simply dissolved in the changed water chemistry. Entire species that had thrived for millions of years vanished from the fossil record almost overnight. The ocean floor became littered with the remnants of ecosystems that could no longer survive in their transformed environment. Yet the surface waters told a completely different story. Warmed by the greenhouse atmosphere and loaded with nutrients from increased rainfall and erosion on land, the upper layers of the ocean became incredibly productive. Algae bloomed in quantities that would dwarf anything we see today. These massive blooms created a feedback loop, absorbing enormous amounts of carbon dioxide while simultaneously releasing oxygen and other gases that further altered atmospheric composition. The color of the oceans themselves changed. Instead of the deep blue we associate with healthy seas, much of the surface water took on greenish and brownish hues from the abundance of microscopic life. From space, if there had been anyone to observe it, Earth would have looked like a different planet entirely. Swirling patterns of green and brown marked vast algae blooms, while the coastlines were completely redrawn by rising sea levels. Sea level rise during this period was dramatic beyond modern comprehension. With no polar ice to lock up water, and with thermal expansion heating the entire ocean column, seas rose by more than 50 meters above current levels. To put this in perspective, that's enough to completely submerge most of Florida, the Netherlands, and vast portions of coastal plains around the world. Cities like New York, London, and Shanghai would have been deep underwater, their locations marked only by shallow tropical seas. This wasn't a temporary flood that receded after a few years. This was a permanent reshaping of continental geography that lasted for hundreds of thousands of years. Entire ecosystems that had evolved on dry land found themselves permanently submerged. But rather than simply destroying these habitats, the rising seas created entirely new types of environments that had never existed before. Shallow inland seas spread across the interiors of continents. What is now the central United States became a vast seaway connecting the Gulf of Mexico to the Arctic Ocean. Similar marine corridors opened across Europe and Asia. These weren't just bodies of water, they were complex ecosystems where fresh water from rivers mixed with salt water from the oceans, creating brackish environments that supported unique communities of life. The marine creatures that evolved in these expanded seas were unlike anything in our modern oceans. Early whales, still retaining some characteristics of their land-dwelling ancestors, began their remarkable evolutionary journey from terrestrial mammals to fully aquatic giants. The warm, nutrient-rich waters provided ideal conditions for these pioneers to experiment with aquatic lifestyles. Fish diversified rapidly in the stable, warm conditions. Without the temperature barriers that exist in our modern oceans, species could migrate freely between what would today be completely separate climate zones. Tropical fish swam in Arctic waters. Temperate species ventured into equatorial seas. The result was a global mixing of marine life that created evolutionary opportunities on an unprecedented scale. Coral reefs, though different from the species we know today, flourished in these warm seas, but they grew in places that would seem impossible now. Coral-like organisms built reefs in waters that today would be far too cold, extending their range almost to the polar regions. These ancient reefs created complex three-dimensional habitats that supported incredible diversity of marine life. The chemistry of these warm seas created some unusual phenomena. In many regions, the water became stratified into distinct layers that didn't mix well. The warm surface waters, rich in oxygen and nutrients, supported abundant life. But the deeper waters, cut off from atmospheric exchange, became depleted of oxygen. These oxygen minimum zones, while hostile to most complex life, became havens for specialized bacteria that could survive without oxygen. These bacterial communities weren't just passive inhabitants of the deep ocean. They actively participated in global chemical cycles, breaking down organic matter and releasing gases like methane and hydrogen sulfide. Some scientists believe these deep-sea bacterial ecosystems may have contributed to the prolonged warming by releasing additional greenhouse gases into the atmosphere. The circulation patterns of these ancient oceans were fundamentally different from what we see today. Without cold polar waters to drive the great conveyor belts of deep ocean circulation, water movement became more sluggish and regional. Instead of the globe-spanning currents that distribute heat and nutrients in our modern oceans, circulation became dominated by local and regional patterns. This change in circulation had profound effects on marine ecosystems. Areas that today receive nutrients from deep water upwelling found themselves cut off from these vital supplies. Conversely, regions that are typically nutrient poor in our modern oceans became incredibly fertile due to different circulation patterns and increased river input from the well-watered continents. The marine food webs that developed during this time were both simpler and more complex than what we see today. Simpler, because the acidified conditions eliminated many shell-building organisms that form crucial links in modern food chains. More complex, because the warm, stable conditions allowed for the evolution of entirely new ecological relationships and feeding strategies. Predation patterns changed dramatically. With abundant prey in the warm surface waters, marine predators could afford to become specialists, evolving highly specific hunting strategies and anatomical adaptations. The fossil record shows evidence of early marine mammals developing echolocation, advanced swimming techniques, and social hunting behaviors during this period. The boundaries between marine and terrestrial environments became blurred as sea levels rose and coastal zones expanded. Vast tidal marshes and mangrove-like ecosystems stretched for hundreds of kilometers inland. These transitional environments became evolutionary laboratories where aquatic and terrestrial species experimented with amphibious lifestyles. Some of the most remarkable evolutionary innovations occurred in these boundary zones. Plants developed new strategies for living in saltwater-influenced soils. Animals evolved ways to move between aquatic and terrestrial environments with increasing efficiency. The genetic innovations that emerged from these experiments would later prove crucial for life's ability to colonize new environments as conditions changed. The seasonal patterns in these ancient oceans were also unique. In our modern world, ocean temperatures vary significantly with the seasons, driving migration patterns and breeding cycles. But in the greenhouse oceans of the Paleocene-Eocene, seasonal temperature variation was minimal. Instead, seasonal patterns were driven more by changes in daylight duration, particularly at high latitudes where the sun disappeared entirely during winter months. This created unusual ecological rhythms. Marine ecosystems at high latitudes had to adapt to months of continuous daylight followed by months of darkness, even though temperatures remained relatively stable throughout the year. Some species developed seasonal migration patterns based on light availability rather than temperature. Others evolved ways to enter dormancy during the dark months, even in warm water. The chemical evolution of seawater during this time left permanent marks that we can still detect today. Sediment cores from deep ocean drilling show distinct layers from this period with unusual chemical signatures. These layers contain elevated levels of carbon isotopes, indicating the massive influx of carbon into ocean systems. They also show evidence of the widespread oxygen depletion that characterized the deep seas. Perhaps most remarkably, these sediment cores reveal that the ocean's chemical transformation wasn't uniform across the globe. Different ocean basins experienced different degrees of acidification and oxygen depletion. Some regions maintained relatively normal conditions, while others became almost uninhabitable for complex life. This patchwork of conditions created a complex mosaic of marine environments, each supporting different communities of specialized organisms. The recovery of ocean chemistry after the peak warming was a slow process that took hundreds of thousands of years. Gradually, as carbon dioxide levels in the atmosphere began to decrease through natural weathering processes, the oceans started to return to more normal pH levels. Deep ocean circulation slowly resumed as slight temperature differences began to develop between different regions. But the oceans that emerged from this transformation were permanently changed. The species that survived carried genetic adaptations that reflected their experience of extreme conditions. Many lineages had developed enhanced tolerance for temperature variation, chemical changes, and low oxygen conditions. These adaptations would prove valuable during future environmental changes throughout Earth's history. The marine ecosystems that recovered were warming, the evolutionary pressure more resilient and diverse than those that existed before the surviving extreme conditions, had created more robust and adaptable species. In many ways, the trauma of the greenhouse oceans had made marine life stronger and more capable of handling environmental stress. As we continue to explore this fascinating period in Earth's history, we'll discover how the atmospheric chemistry itself became a driving force of change, how weather patterns reorganized on a global scale, and how the interaction between land, sea, and air created feedback loops that sustained the warming for hundreds of thousands of years. The story of these ancient greenhouse oceans isn't just about marine life adapting to change. It's about how planetary systems can reorganize themselves in ways that seem almost impossible until they happen. The lessons written in the chemistry of ancient seawater and preserved in ocean sediments tell us that even the most extreme changes in Earth's systems are survivable, though they require adaptations that can take millions of years to develop. As our own oceans begin to warm and acidify in ways that echo this ancient transformation, understanding how marine life navigated these challenges before becomes crucial for predicting what might happen next. The atmosphere itself became something alien during this ancient greenhouse period. While we've explored how forest scenes colonized the poles and OCD beyond recognition, the very air that surrounded our planet underwent changes so profound that breathing would have felt different, looked different, and carry a world we can sense from barely imagined today dioxide levels. So, carbon aired to concentrations that dwarf anything in human experience, where today we measure atmospheric carbon dioxide at around 400 parts per million, during the Paleocene-Eocene thermal maximum, levels reach nearly 2,000 parts per million. That's not just a number on a scientific chart. It represents a fundamental shift in how energy moved through Earth's systems. Think of the atmosphere as a blanket wrapped around our planet. Normally, this blanket allows sunlight to pass through easily while letting some heat escape back to space. But when carbon dioxide concentrations quadruple, that blanket becomes incredibly thick and efficient at trapping warmth. Infrared radiation that would normally escape into the cold of space gets caught, absorbed, and re-radiated back toward Earth's surface. The planet essentially developed a fever that fed on itself. But carbon dioxide wasn't acting alone. Methane, an even more potent greenhouse gas, began seeping from sources across the globe. Warming soils released methane that had been locked in permafrost. Ocean sediments, destabilized by rising temperatures, burped up massive quantities of methane that had been trapped in ice-like structures called hydrates. Some scientists believe this methane release created a runaway effect where warming triggered more methane release, which caused more warming in an escalating spiral that lasted for millennia. The air itself became visibly different. With so much moisture evaporating from the warm oceans, humidity levels reached extremes that would feel oppressive to anyone accustomed to modern climates. The atmosphere could hold vast quantities of water vapor, itself a greenhouse gas, creating a feedback loop where heat generated more humidity, which trapped more heat. Clouds formed differently, creating patterns in the sky that nod. Whether human has ever witnessed systems during this time operated under completely different rules, without the temperature gradient between poles and equator that drives our modern atmospheric circulation, the familiar patterns of trade winds, jet streams, and seasonal storm tracks simply didn't exist. Instead, the atmosphere organized itself into circulation patterns that seem almost impossible to our modern understanding. Massive thunderstorm systems, potentially larger and more persistent than anything in recorded history, may have dominated tropical regions. These weren't ordinary storms, but atmospheric monsters powered by the enormous energy trapped in the superheated air and oceans. They could have towered higher into the atmosphere than modern storms ever reach, creating vertical columns of turbulence that mixed gases and particles across altitude levels that normally remain separate. The chemistry of rainfall changed dramatically. Water evaporating from the warm oceans carried different isotopic signatures than modern precipitation. When this moisture condensed and fell as rain, it delivered chemical information about ocean temperatures directly to the land surface. Trees growing during this period absorbed this chemically distinct water, leaving isotopic fingerprints in their wood that we can still analyze today. Dust and particles moved through this thick atmosphere in unusual ways. Volcanic eruptions, which may have helped trigger the initial warming, sent ash and sulfur compounds into air that was already dense with moisture and greenhouse gases. These particles interacted with the atmospheric chemistry in complex ways. Sunlight, other times in sometimes cooling regions temporarily, by blocking the greenhouse effect, by trapping additional heat. The very act of photosynthesis accelerated under these conditions. Plants were essentially living in a world of unlimited atmospheric fertilizer. Carbon dioxide levels that would stress modern vegetation instead supercharged ancient plant growth. Leaves grew larger and thicker to take advantage of the abundant carbon dioxide. Forests became denser and more productive than anything we see today. This atmospheric abundance had cascading effects throughout ecosystems. Herbivores found themselves in a world where food was not just plentiful, but more nutritious. The enhanced photosynthesis meant plants could produce more sugars, proteins, and other compounds that animals depended on. Food webs became more complex and interconnected as energy flowed more freely through natural systems. But the atmosphere's transformation also created challenges that pushed evolution in unexpected directions. The thick, humid air carried less oxygen per breath than thinner, drier air. Animals had to develop more efficient respiratory systems or accept lower activity levels. Some species evolved larger lung capacities or more efficient oxygen transport systems. Others adapted by slowing their metabolisms and becoming less active during the hottest parts of the day. Sound traveled differently through this dense, humid air. The calls of animals, the rustle of vegetation, even the sound of wind moving through forests would have had different acoustic properties. Communication between animals may have evolved to account for these changed sound transmission characteristics. Some species might have developed new vocal strategies to cut through the atmospheric density. The interaction between this transformed atmosphere and solar radiation created optical effects that no modern human has witnessed. Sunsets and sunrises, filtered through air heavy with moisture and particles, would have painted the sky in colors and patterns unlike anything we see today. The sun itself may have appeared different, its light scattered and filtered by atmospheric conditions that existed nowhere else in Earth's recent history. Atmospheric pressure increased as the air became denser with greenhouse gases and water vapor. This higher pressure affected everything from how water boiled to how animals' circulatory systems functioned. Creatures living during this time had to adapt to an environment where the very weight of the air pressing down on them was different from what their ancestors had experienced. The seasonal patterns of atmospheric behavior were unlike anything in our modern world. In regions where day length varied dramatically with the seasons, the atmosphere had to adjust to months of continuous daylight, followed by months of darkness. During polar summer, the endless sunshine drove continuous evaporation and weather activity. During polar winter, the atmosphere had to redistribute heat without the driving force of solar energy, creating circulation patterns that existed nowhere else in Earth's climate system. Chemical reactions in this altered atmosphere proceeded at different rates than they do today. The elevated temperatures and changed gas concentrations meant that natural processes of atmospheric chemistry accelerated. Compounds that normally persist for long periods broke down more quickly. Others formed more readily. The entire atmospheric chemistry became a faster, more dynamic system. This atmospheric transformation wasn't just a passive backdrop to the biological changes happening on land and in the oceans. It was an active participant in driving evolution and ecological change. Species that could tolerate or even thrive in the changed atmospheric conditions gained advantages over those that couldn't adapt. The atmosphere itself became a selective pressure that shaped the direction of evolutionary change. The recovery of atmospheric chemistry after the peak warming was a gradual process that took hundreds of thousands of years. Natural weathering processes slowly pulled carbon dioxide out of the air and locked it into rock formations. The abundance of vegetation growing in the enhanced greenhouse conditions eventually began to draw down atmospheric carbon through photosynthesis and burial of organic matter. But even as carbon dioxide levels began to decrease, the atmosphere retained memory of its greenhouse phase. The circulation patterns that developed during the warming persisted long after temperatures began to moderate. Weather systems that evolved under extreme conditions continued to influence climate patterns for millions of years. The atmospheric legacy of the greenhouse period shaped Earth's climate system far beyond the warming event itself. Volcanic activity during this time added another layer of complexity to atmospheric chemistry. Eruptions released not just carbon dioxide, but also sulfur compounds, ash, and trace gases that interacted with the existing greenhouse atmosphere in unpredictable ways. Some volcanic emissions temporarily cooled local regions by blocking sunlight. Others enhanced warming by adding more greenhouse gases to an already saturated system. The atmospheric chemistry of this period created conditions that allowed for unprecedented biological productivity. The combination of high carbon dioxide, elevated temperatures, and abundant moisture created environments where life could flourish in ways that seem almost impossible by modern standards. Forests grew faster and denser. Ocean productivity soared. Evolution accelerated as species adapted to the abundance of energy flowing through natural systems. Understanding this atmospheric transformation helps us grasp the scale of change that's possible when greenhouse gas concentrations shift dramatically. The same physics that governed atmospheric behavior 56 million years ago still operates today. The difference lies in the speed of change. What took thousands of years during the ancient warming is now happening in decades, creating challenges for atmospheric systems that evolve to change gradually over geological timescales. The lessons preserved in ice cores, sediment layers, and fossilized organic matter tell us that atmospheric chemistry is not just a backdrop to life on Earth, but an active participant in shaping evolutionary history. The greenhouse atmosphere of the Paleocene-Eocene didn't just warm the planet, it created opportunities for biological innovation and diversification that might never have occurred under more stable conditions. As we continue exploring this remarkable period, we'll discover how these atmospheric changes drove the evolution of intelligence itself, how early mammals developed the cognitive abilities that would eventually lead to consciousness, and how the pressure of surviving in a rapidly changing world created the neural innovations that define modern animal behavior. The story of this ancient greenhouse atmosphere isn't just about chemistry and physics. It's about how environmental challenge becomes the raw material for evolutionary breakthrough. As these atmospheric changes intensified, something remarkable began happening in the brains of early mammals. The cognitive pressures of surviving in such a rapidly changing world weren't just shaping bodies and behaviors. They were literally rewiring neural pathways and expanding mental capabilities in ways that would echo through millions of years of evolution. Picture the challenges facing a small mammal during this greenhouse period. Traditional food sources disappeared as ecosystems shifted. Seasonal patterns that ancestors had relied on for generations became unreliable or vanished entirely. Migration routes that had worked for millions of years suddenly led to environments that no longer existed. The cognitive demands of navigating this transformed world pushed mammalian brains to develop new capacities for learning, memory, and problem-solving. Early primates swinging through those expanded polar forests faced particularly complex challenges. Dense canopies required sophisticated spatial reasoning to navigate safely between branches. Fruit and food sources were abundant, but distributed unpredictably across vast forested areas. Social groups became larger and more complex as resources allowed for bigger populations, but this meant keeping track of more relationships, hierarchies, and alliances. The neurological innovations that emerged during this period weren't just about individual survival. They were about developing the capacity to predict, plan, and adapt to environments that changed faster than genetic evolution could keep pace with. Brains that could learn new behaviors within a single lifetime gained enormous advantages over those locked into instinctual responses that might no longer be relevant. Memory systems became more sophisticated as animals needed to track resources across larger territories and more complex seasonal cycles. The hippocampus, that crucial brain region responsible for spatial navigation and memory formation, expanded in many mammalian lineages during this time. Creatures needed to remember not just where food was located, but how to get there through forest canopies that might extend unbroken for thousands of kilometers. Communication systems evolved rapidly as well. In environments where visibility was limited by dense vegetation and where acoustic properties changed due to humid atmospheric conditions, animals developed more complex vocalizations and social signals. Early primates began using different calls for different types of threats, food discoveries, and social situations. The cognitive infrastructure for language was being built, one neural innovation at a time. The abundance of food during this greenhouse period paradoxically created new intellectual challenges. With survival needs more easily met, animals had energy and time to invest in activities beyond immediate necessity. Play behavior became more complex and extended. Young mammals spent longer periods learning from adults. Social structures grew more intricate, as groups could support individuals who specialized in different roles. Tool use, though still primitive, began appearing in some lineages during this time. Not the sophisticated stone tools that would come much later, but simple applications of sticks, stones, and plant materials to solve immediate problems. The cognitive leap required to see an object as a potential tool, to imagine its use before actually employing it, represents a fundamental shift in mental capability that traces back to this period of environmental challenge and abundance. The sensory systems of mammals also underwent dramatic enhancement during the greenhouse period. In dense forests where visual cues might be obscured, hearing and smell became more acute. Some species developed the ability to echolocate, using sound waves to navigate through complex three-dimensional environments. Others enhanced their chemical sensing capabilities, using scent to track resources and communicate across distances that would be impossible with visual signals alone. Perhaps most importantly, the greenhouse period saw the emergence of what we might call metacognition, the ability to think about thinking itself. Animals began developing the capacity to monitor their own mental states, to recognize when they didn't know something and needed to learn it. This self-awareness, though still rudimentary, became the foundation for all future cognitive evolution. The social implications of these neural developments were profound. Groups became more cooperative and coordinated as individuals developed better abilities to understand and predict the behavior of others. Empathy, the capacity to model another individual's mental state, began emerging as a crucial social skill. Animals that could anticipate what their companions might do gained advantages in everything from hunting to avoiding predators. Parental care became more sophisticated as adult brains developed better capacities for understanding the needs and developmental stages of their offspring. Teaching behaviors emerged, where adults actively demonstrated skills to young, rather than simply allowing them to observe and imitate. The extended period of abundant resources meant that juveniles could afford longer periods of learning and brain development. These cognitive innovations weren't distributed evenly across all mammalian species. The lineages that invested most heavily in brain development, particularly those that would eventually give rise to primates, dolphins, and elephants, gained disproportionate advantages in the complex environments of the greenhouse world. Intelligence became a survival strategy that could adapt faster than genetic change, allowing these lineages to thrive across a broader range of conditions. The neural plasticity that developed during this period, the brain's ability to rewire itself in response to new experiences, became one of the most important evolutionary innovations in Earth's history. Instead of being locked into genetically determined behavioral patterns, mammals developed the capacity to learn new responses to novel situations within their own lifetimes. This flexibility would prove crucial not just during the greenhouse period, but during all subsequent environmental changes. Dream sleep, that mysterious state where brains process and consolidate memories, became more complex during this time. The increased cognitive demands of navigating changing environments meant that sleep patterns evolved to provide more time for neural processing and memory formation. The dreams of these ancient mammals, though we can only speculate about their content, likely reflected the cognitive challenges of living in a world where nothing stayed the same for long. Emotional systems also grew more nuanced as social groups became larger and more complex. The ability to form lasting bonds with multiple individuals, to maintain relationships across time and distance, to experience grief, joy, and anticipation, all emerged or intensified during this period of rapid environmental change. Emotional intelligence became as important as analytical intelligence for navigating the social complexities of greenhouse world communities. The greenhouse atmosphere itself may have influenced brain development in direct ways. Higher oxygen levels in some regions, combined with the enhanced nutrition available from supercharged plant growth, provided the metabolic resources necessary to support larger, more energy-intensive brains. The cognitive revolution of this period was supported by the same environmental abundance that drove ecological transformation. These neural innovations created feedback loops that accelerated further cognitive development. Smarter animals were better at finding and exploiting resources, which supported larger populations and more complex social structures, which in turn created pressures for even greater intelligence. The greenhouse period became an evolutionary arms race where cognitive capability drove survival success. The legacy of these ancient neural innovations shapes every intelligent creature on Earth today. The capacity for learning, memory, social cooperation, and environmental adaptation that we see in modern mammals all trace their origins back to the cognitive challenges of surviving in a rapidly changing greenhouse world. The same environmental pressures that transformed forests and oceans also transformed minds. As the greenhouse period progressed and environments continued to shift, these cognitive innovations proved their worth time and again. Species that had invested in brain development survived environmental changes that eliminated less adaptable lineages. Intelligence became not just a survival tool, but the foundation for all future evolutionary success in a world where change was the only constant. But even as life was adapting and innovating on land, the rising seas were creating their own evolutionary laboratories. The same warming that challenged terrestrial creatures was literally reshaping the boundaries between land and water, creating vast new environments where the rules of survival would be written from scratch. The coastlines of the greenhouse Earth were unlike anything we can imagine today. Instead of the relatively narrow tidal zones we're familiar with, the boundaries between land and sea stretched for hundreds of kilometers inland. These weren't simple beaches or rocky shores, but vast transitional ecosystems where saltwater mixed with fresh, where marine creatures ventured onto land, and where terrestrial animals began their first tentative explorations of aquatic life. Picture endless shallow seas dotted with islands of vegetation, where mangrove-like forests created three-dimensional mazes of roots, branches, and waterways. These weren't true mangroves, which hadn't evolved yet, but their ecological predecessors, plants that had learned to tolerate salt and thrive in the boundary zone between terrestrial and marine environments. Their root systems created underwater forests that provided shelter and breeding grounds for countless species. The chemistry of these coastal waters was unique, a constantly shifting blend of ocean saltwater and freshwater runoff from the well-watered continents. This created gradients of salinity that changed with tides, seasons, and rainfall patterns. Animals living in these environments had to develop remarkable physiological flexibility, capable of handling dramatic changes in water chemistry within their own lifetimes. Some of the most remarkable evolutionary innovations occurred in these boundary zones. Amphibious mammals began developing the anatomical and physiological adaptations that would eventually lead to fully aquatic whales. Their limbs started elongating and flattening into more efficient swimming appendages. Their nostrils began migrating toward the tops of their heads. Their bones became denser to help with underwater locomotion. These early whale ancestors weren't making a sudden leap from land to sea. Instead, they were gradually exploring deeper and deeper water, spending more and more time submerged, following food sources that were abundant in the warm coastal waters. Each generation became slightly more aquatic than the last, in an evolutionary journey that would transform land mammals into the largest creatures ever to inhabit Earth. Fish populations exploded in these expanded coastal environments. The warm, nutrient-rich waters provided ideal breeding conditions for countless marine species. Schools of fish grew to sizes that would dwarf anything in our modern oceans, creating feeding opportunities for marine predators that drove rapid evolutionary diversification. Early sharks and other predatory fish evolved new hunting strategies to exploit these abundant prey populations. The boundaries between different types of aquatic environments became blurred as sea levels rose. Freshwater lakes connected to brackish estuaries, which flowed into shallow seas, which deepened into open ocean. Fish that had been confined to specific salinity ranges found themselves in environments where they could gradually adapt to different water chemistry. This led to remarkable evolutionary flexibility as species developed tolerance for a wide range of aquatic conditions. Coral-like organisms thrived in these warm, shallow seas, but they built reefs in patterns completely different from anything we see today. Without the temperature limitations that constrain modern corals to tropical regions, these reef-building creatures spread into waters that would now be far too cold for them. They created massive three-dimensional structures that provided habitat for incredible diversity of marine life. The tidal ranges in these ancient seas were different from what we experience today. With higher overall sea levels and different continental configurations, tides could penetrate much farther inland than they do now. Vast areas experienced regular cycles of flooding and exposure that created unique intertidal ecosystems. Plants and animals in these zones had to survive being submerged for hours at a time, then exposed to air and sunlight when waters receded. Marine reptiles, the last remnants of groups that had dominated seas during the age of dinosaurs, found new opportunities in these warm waters. Some species experienced evolutionary renaissance, adapting to the changed conditions and diversifying into forms not seen before or since. These ancient marine reptiles shared the seas with early marine mammals, creating competitive pressures that drove innovation in both groups. The acoustic environment of these coastal waters was unique. Sound travels differently through water of varying temperature and salinity. Marine mammals developing echolocation abilities had to adapt their vocalizations to work effectively in water that might change chemistry dramatically over short distances. This may have driven the evolution of more sophisticated and flexible acoustic communication systems. Plankton communities in these coastal waters were unlike anything in modern oceans. The combination of warm temperatures, abundant nutrients from land runoff, and stable conditions created massive blooms of microscopic life. These organisms formed the foundation of food webs that supported incredible abundance and diversity of larger marine creatures. The water itself often took on greenish or brownish hues from the density of microscopic life. Bottom-dwelling creatures adapted to life in sediments that were constantly being disturbed by the activities of countless other organisms. Burrowing animals developed new strategies for maintaining their tunnels and burrows in substrates that were alive with activity. filter-feeding organisms evolved more efficient ways to extract nutrients from water that was thick with organic matter. The seasonal patterns in these coastal environments were driven more by changes in daylight duration than temperature variation. At high latitudes, marine ecosystems had to adapt to months of continuous daylight, followed by months of darkness, even though water temperatures remained relatively stable. This created unique ecological rhythms, where breeding, feeding, and migration patterns were synchronized to light availability rather than thermal cycles. Migration patterns of marine animals during this period spanned greater distances than anything we see today. With warm waters extending from equator to poles, some species may have undertaken journeys that circumnavigated the entire globe. These migrations created genetic mixing on a planetary scale, contributing to the rapid evolutionary diversification characteristic of the greenhouse period. The chemistry of coastal sediments changed as vast quantities of organic matter accumulated in shallow waters. Dead plankton, plant material, and animal remains settled into sediments at rates that far exceeded modern deposition. These organic-rich layers would eventually become some of the oil and gas deposits that modern humans extract for energy. But during the greenhouse period, they were active components of coastal ecosystems. Symbiotic relationships between different species became more complex in these productive coastal environments. With abundant energy flowing through marine food webs, animals could afford to invest in cooperative relationships that might not be viable under more resource-limited conditions. Some of the most sophisticated partnerships between different species may have first evolved in the abundant coastal waters of the greenhouse period. The transition zones where rivers met the sea became particularly important evolutionary laboratories. Here, freshwater species encountered marine environments gradually, allowing for step-by-step adaptation to saltwater conditions. Some fish species that made this transition successfully became the ancestors of groups that would later colonize a wide range of aquatic environments. As these coastal ecosystems matured and stabilized, they created feedback effects that influenced the broader climate system. Vast areas of shallow, warm water released enormous quantities of water vapor into the atmosphere, contributing to the greenhouse effect that maintained global warmth. The biological productivity of these coastal zones also helped regulate atmospheric chemistry by absorbing and releasing gases that affected global temperature patterns. The legacy of these ancient coastal environments can still be seen in the evolutionary history of modern marine life. Many of the anatomical and physiological innovations that allow current marine mammals to thrive in ocean environments first appeared in the boundary zones of the greenhouse period. The flexibility and adaptability that characterizes successful marine life today was forged in the evolutionary crucible of those ancient transitional ecosystems. But the same processes that created these abundant coastal environments were also setting the stage for their eventual transformation. The chemistry that supported such incredible marine productivity was slowly changing as natural weathering processes began to draw carbon out of the atmosphere. The fever that had reshaped the planet was beginning its slow recovery, though the changes it had wrought would influence life on Earth for millions of years to come. The recovery from this ancient greenhouse period wasn't a simple return to previous conditions. Instead, it represented a fundamental reorganization of Earth systems that created new possibilities for life while closing off others. As we'll discover, the cooling that eventually followed the extreme warming brought its own evolutionary challenges and opportunities, shaping the planet toward the more familiar patterns of climate and life that would eventually give rise to our modern world. The slow drawdown of carbon from that ancient greenhouse atmosphere wasn't dramatic or sudden. There was no moment when the fever broke, no clear signal that the planet had reached its tipping point toward recovery. Instead, it was the patient work of chemistry and time, processes so gradual that no creature alive during those epochs would have noticed the change happening around them. Rain fell on exposed rock faces, just as it always had. But now, there was more rock to weather, more surface area exposed by the geological processes that never stop reshaping continents. As water mixed with carbon dioxide in the air, it formed weak carbonic acid that slowly dissolved minerals from stone. This wasn't destruction, it was transformation. The carbon that had been heating the atmosphere was gradually being locked away in chemical reactions, stored in new mineral formations that would hold it for millions of years. The forests that had exploded across the globe during the peak warming played their own crucial role in this recovery. Trees that had grown enormous in the carbon-rich air were now dying, falling, and being buried in sediments that accumulated in river deltas and shallow seas. Each fallen giant represented tons of carbon pulled from the atmosphere and stored in what would eventually become coal seams and organic-rich rock layers. Ocean chemistry began its own slow rebalancing act. The acidic waters that had dissolved so many shell-building creatures gradually became less hostile as carbon dioxide concentrations in the atmosphere decreased. Marine organisms that had survived in refugia, small pockets of more tolerable conditions, began to expand their ranges again. New species of shell builders evolved, often with thicker, more resilient structures that could better withstand chemical stress. Volcanic activity, which may have helped trigger the initial warming, began to subside. The massive eruptions that had released carbon stored in seafloor sediments became less frequent and less intense. Without this constant input of greenhouse gases, the natural processes of carbon removal could finally begin to outpace carbon emissions. The planetary thermostat started its slow adjustment toward cooler settings. The poles, those tropical wonderlands that had supported forests for hundreds of thousands of years, began to feel the first hints of seasonal variation returning to their climate. It wasn't sudden cooling, but rather a gradual strengthening of the temperature differences between summer and winter. Some tree species that had thrived in the constant warmth began to struggle with even minor temperature fluctuations. This wasn't the beginning of an ice age, but rather the first steps toward a more moderate greenhouse climate. The world would remain warm by modern standards for millions of years to come, but the extreme conditions that had characterized the thermal maximum were slowly giving way to something more stable and predictable. Animal migration patterns began to shift as these subtle temperature changes created new environmental gradients. Species that had spread freely across the globe during the period of uniform warmth started to encounter barriers again. Some populations became isolated and began evolving in different directions, creating the first steps toward the biological diversity patterns we see in modern ecosystems. The atmospheric circulation patterns that had been disrupted by the extreme warming began to reorganize themselves. The temperature difference between equator and poles, though still small compared to modern conditions, was enough to restart some of the familiar patterns of wind circulation. Trade winds began to re-establish themselves. The first hints of seasonal weather patterns started to emerge. Ocean currents, those great conveyor belts of heat and nutrients, slowly resumed more normal circulation patterns. As slight temperature differences developed between different regions, density differences in seawater began to drive mixing between surface and deep waters. The oxygen-starved deep ocean zones gradually became more habitable as circulation brought fresh, oxygenated water from the surface. The recovery wasn't uniform across the globe. Some regions cooled faster than others, creating a patchwork of different climate zones that hadn't existed during the peak warming. This environmental heterogeneity drove evolutionary innovation as species adapted to local conditions, rather than the global uniformity that had characterized the greenhouse world. Coral reef ecosystems, having survived the worst of the acidification in small refugees, began to expand again as ocean chemistry improved. But the reefs that grew during the recovery were different from those that had existed before the warming. They were built by new species that had evolved greater tolerance for chemical and temperature stress, creating more resilient ecosystems. The massive algae blooms that had colored the oceans green and brown during the peak warming began to subside as nutrient inputs from land decreased and marine food webs rebalanced themselves. Clearer waters allowed sunlight to penetrate deeper, supporting the growth of bottom-dwelling plants and the organisms that depended on them. Sea levels, which had remained high throughout the warming period, began their imperceptible decline as the first ice began to form in high-altitude and high-latitude regions. This wasn't the return of massive ice sheets, but rather the formation of small glaciers in mountain ranges and seasonal ice in polar regions. The process would take millions of years, but the productive during the warming face direction of change had shifted. Coastal ecosystems that had been incredibly ived in the abundance of the greenhouse period, new challenges as their environments became less stable. Some species that had thrived couldn't adapt to the increasing variability of conditions. Others found opportunities in the new ecological niches that were opening up as climate zones began to differentiate again. The cognitive innovations that had emerged in mammalian brains during the challenging greenhouse period proved their worth during the recovery. Species with enhanced learning abilities and behavioral flexibility were better able to adapt to changing conditions than those locked into rigid behavioral patterns. Intelligence became an increasingly important survival tool as environmental predictability decreased. Plant communities that had been dominated by fast-growing high-temperature species began to include more diverse assemblages as cooler-adapted plants found niches in the changing climate. Forest composition shifted gradually, with some species becoming more common, while others retreated to refugia, where conditions remained favorable for their growth requirements. The chemical signatures of this recovery period are preserved in sediment cores and rock formations around the world. Scientists can trace the gradual decline in carbon isotopes that marks the slow removal of greenhouse gases from the atmosphere. These records show that the recovery wasn't a simple reversal of the warming, but rather a complex reorganization of Earth's carbon cycle. Marine sediments from this period show the gradual return of calcium carbonate-shelled organisms as ocean acidity decreased. The layers tell a story of ecosystem recovery and reorganization, with new species appearing while others disappeared from the fossil record. It's a testament to life's resilience and adaptability in the face of major environmental change. The recovery period saw the emergence of more complex food webs as environmental conditions stabilized enough to support specialized ecological relationships. Predator-prey dynamics became more intricate, and symbiotic relationships between different species became more sophisticated. The simple abundance of the greenhouse period gave way to more nuanced ecological interactions. Weather patterns during the recovery became more variable and seasonal, creating selective pressures that hadn't existed during the stable greenhouse period. Animals had to develop strategies for dealing with unpredictable conditions, leading to innovations in behavior, physiology, and social organization that would influence evolutionary trajectories for millions of years. The transition from greenhouse to more moderate conditions created evolutionary opportunities for lineages that had been suppressed during the extreme warming. Some groups that had survived in small populations or marginal habitats began to diversify and expand as conditions became more favorable for their particular adaptations. Atmospheric composition continued to change gradually throughout the recovery period. Water vapor levels decreased as temperatures moderated, reducing one of the important feedback mechanisms that had maintained the greenhouse conditions. Cloud formation patterns changed, affecting regional climate patterns and creating new environmental gradients. The soils that had developed under greenhouse conditions began to change as temperature and precipitation patterns shifted. New mineral weathering patterns created different nutrient availabilities, influencing plant communities and the animals that depended on them. Soil organisms adapted to changing chemical conditions, altering decomposition rates and nutrient cycling. River systems that had been swollen by heavy rainfall during the greenhouse period began to adjust to more moderate precipitation patterns. Channel patterns changed. affecting the organisms that lived in and around freshwater systems. Some aquatic species that had thrived during the high-flow conditions had to adapt to more variable water levels. The recovery from the ancient greenhouse period demonstrates one of Earth's most remarkable characteristics, its ability to self-regulate through feedback mechanisms that operate over geological timescales. The same processes that had amplified the initial warming eventually began to counteract it, showing how planetary systems tend toward balance even after extreme perturbations. This slow return to climatic stability set the stage for the next chapter in life's evolutionary story. The species that emerged from the greenhouse period were fundamentally different from those that had entered it. They carried genetic and behavioral innovations that had been forged in the crucible of rapid environmental change, adaptations that would prove crucial for surviving future climate fluctuations. The ecosystems that developed during the recovery were more resilient and diverse than those that had existed before the warming event. The evolutionary pressure of surviving extreme conditions had created more robust biological communities capable of withstanding environmental stress. In many ways, the greenhouse period and its recovery had made life on Earth stronger and more adaptable. As the planet slowly cooled from its fever and atmospheric chemistry gradually normalized, the stage was being set for the emergence of more familiar climate patterns. The recovery wasn't just a return to previous conditions, but rather the birth of new possibilities for how life could organize itself on a changing planet. The lessons preserved in this ancient recovery offer profound insights into how Earth's systems respond to major perturbations. They show us that while change can be dramatic and disruptive, natural processes tend toward rebalancing over time. The question for our modern world isn't whether the planet can recover from climate change, but how long that recovery might take and what forms life might take during the process. The story of how Earth healed from its ancient fever continues to unfold in the rocks beneath our feet and the chemistry of ancient atmospheres trapped in ice. It's a story of resilience, adaptation, and the extraordinary capacity of life to not just survive change, but to use it as fuel for innovation and diversification. And as we face our own period of rapid climate change, understanding this ancient recovery becomes crucial for imagining what kinds of worlds might emerge from our current environmental transformation. The cooling that followed the greenhouse period wasn't uniform or predictable. Instead, it created a complex mosaic of environmental conditions that would challenge life in new ways while opening up unprecedented evolutionary opportunities. As we'll discover, this transition period would witness some of the most remarkable innovations in the history of life on Earth, adaptations that would eventually give rise to the familiar world we inhabit today. As this gradual cooling continued to reshape the planet, something extraordinary was happening in the evolutionary laboratories created by these changing conditions. The transition from greenhouse to more moderate climates wasn't just selecting for survivors. It was actively creating new forms of life that would become the foundation for everything that followed. The mammals that had diversified so dramatically during the peak warming now found themselves in a world of increasing environmental complexity. Where once uniform heat had allowed species to spread freely across the globe, now temperature gradients were creating barriers and opportunities in equal measure. Some populations became isolated as climate zones began to separate, while others discovered new ecological niches opening up in the transitional environments. This geographic isolation became one of evolution's most powerful tools. Groups of animals that had been part of single, widespread populations during the greenhouse period suddenly found themselves cut off from their relatives by expanding areas of unsuitable habitat. Each isolated population faced slightly different environmental pressures, and over thousands of generations, these small differences accumulated into major evolutionary innovations. In the forests that were slowly retreating from the poles, early primates faced new challenges that would literally reshape their minds. The endless canopies of the greenhouse period were fragmenting into patches separated by more open habitats. Moving between these forest islands required enhanced spatial reasoning, better memory for landmark navigation, and more sophisticated social coordination when traveling in groups. These cognitive demands drove rapid brain evolution in primate lineages. The regions responsible for spatial processing, memory formation, and social cognition expanded dramatically. Tool use, which had been rudimentary during the greenhouse period, became more sophisticated as primates learned to use objects to bridge gaps between trees or extract food from difficult locations. The foundations of intelligence as we understand it were being laid in response to a fragmenting world. Meanwhile, in the grasslands that were beginning to appear as forests thinned, a completely different set of evolutionary pressures was shaping mammalian development. The ancestors of modern grazing animals found themselves in open environments where speed and endurance mattered more than climbing ability or fine motor control. Their limbs lengthened, their bodies streamlined, and their digestive systems adapted to process the tougher vegetation that grew in these drier conditions. Predators followed their prey into these new grassland environments, but hunting in open spaces required different strategies than stalking through dense forests. Pack hunting behaviors evolved as individual predators found they could bring down larger prey by coordinating their attacks. Communication systems became more sophisticated as hunters learned to coordinate movements across distances where visual contact wasn't always possible. The ocean currents that were slowly reorganizing themselves created marine highways that some species learned to exploit for long-distance travel. Early whales, now fully committed to aquatic life, began following these currents on migrations that spanned entire ocean basins. Their brains evolved enhanced navigation capabilities, possibly including magnetic sensing abilities that allowed them to maintain course across thousands of kilometers of open water. The seasonal patterns that were becoming more pronounced in many regions created new evolutionary pressures that hadn't existed during the stable greenhouse period. Animals had to develop strategies for surviving periods of scarcity that alternated with times of abundance. Some species evolved the ability to store fat during good times to sustain them through lean periods. Others developed migration behaviors that allowed them to follow favorable conditions as they shifted across the landscape. Plant communities were undergoing their own revolutionary changes as climate zones became more distinct. The carbon dioxide levels that had supercharged plant growth during the greenhouse period were slowly declining, forcing vegetation to become more efficient at capturing and using atmospheric carbon. Leaves evolved more complex internal structures, root systems became more extensive, and symbiotic relationships with soil fungi became more sophisticated. The boundaries between different plant communities became sharper as environmental gradients strengthened. Forest edges, grassland margins, and wetland borders became zones of intense evolutionary activity where species from different habitats came into contact and competition. Hybrid zones emerged where different plant types could interbreed, creating new combinations of traits that might prove advantageous under changing conditions. Insect evolution accelerated dramatically during this transition period. The diversification of plant communities created countless new ecological niches for herbivorous insects, each plant species potentially supporting specialized insect communities. Pollinating insects co-evolved with flowering plants in an intricate dance that would eventually give rise to some of the most complex ecological relationships on Earth. The cooling climate created altitude gradients that hadn't been significant during the uniform warmth of the greenhouse period. Mountain slopes became elevational laboratories where species could adapt to different temperature and moisture conditions within relatively small geographic areas. This vertical zonation allowed for rapid evolutionary experimentation as populations at different elevations faced distinct selective pressures. Aquatic environments became more diverse as temperature differences between regions strengthened. Lakes and rivers in different climate zones developed distinct communities of organisms adapted to local conditions. Some fish species that had been widespread during the greenhouse period began to diverge into multiple species as populations in different water bodies adapted to local environmental conditions. The marine realm saw its own complex reorganization as ocean currents strengthened and temperature gradients became more pronounced. Upwelling zones, where deep, nutrient-rich water rises to the surface, became more active and predictable. These areas of enhanced productivity became focal points for marine evolution, supporting dense communities of organisms that evolved specialized adaptations for exploiting concentrated food sources. Coral reef ecosystems, recovering from the acidification of the greenhouse period, began to develop the complex three-dimensional structures we associate with modern reefs. The cooler temperatures and improved water chemistry allowed for more intricate calcium carbonate construction, creating habitat complexity that supported incredible diversity of marine life. Symbiotic relationships between corals and algae became more sophisticated, allowing reef systems to thrive in nutrient-poor tropical waters. The atmospheric chemistry changes that accompanied cooling had direct effects on animal physiology. As oxygen levels fluctuated and atmospheric pressure changed, respiratory systems had to adapt to varying gas availability. Some lineages developed more efficient lungs or oxygen transport systems, while others adapted by slowing their metabolisms or changing their activity patterns. Bird evolution took off during this transition period, literally and figuratively. The changing landscape created numerous opportunities for flying creatures to exploit resources that were separated by distances too great for terrestrial animals to cover efficiently. Wing shapes diversified as different species adapted to different flight styles, from the soaring flight needed to cross vast grasslands to the maneuverable flight required for navigating through fragmented forests. The development of more distinct seasons created opportunities for behavioral innovations that would become hallmarks of advanced animal intelligence. Migration timing became crucial as animals learned to anticipate seasonal changes and prepare for long-distance movements. Some species developed the ability to delay reproduction until conditions were most favorable, requiring sophisticated internal timing mechanisms. Social structures became more complex as environmental unpredictability made cooperation increasingly valuable. Animals that could share information about resource locations, coordinate group movements, or collectively defend against predators had advantages over more solitary species. The cognitive demands of maintaining these social relationships drove further brain evolution, particularly in regions associated with social cognition and communication. The transition period also saw the emergence of more specialized ecological roles. During the greenhouse period, many species had been generalists capable of exploiting a wide range of resources. As environments became more differentiated, there were advantages to specializing in particular food sources or habitat types. This specialization led to the evolution of highly efficient anatomical and physiological adaptations for specific lifestyles. Energy budgets became more important as environmental conditions became less predictable. Species evolved more sophisticated mechanisms for conserving energy during periods of scarcity and efficiently exploiting resources when they were available. This led to innovations in metabolism, body size optimization, and behavioral strategies that maximized energy efficiency. The fossil record from this transition period shows evidence of rapid evolutionary experimentation. Many lineages appear to have tried multiple different adaptive strategies, with some becoming evolutionary dead ends, while others led to major new groups of organisms. This pattern of rapid diversification, followed by selective survival, is characteristic of evolutionary adaptive radiations. Chemical communication became more sophisticated as species adapted to environments where visual and acoustic signals might be less reliable. Scent marking, pheromone production, and chemical recognition systems evolved greater complexity and specificity. Some species developed the ability to convey complex information about identity, reproductive status, and territorial boundaries through chemical signals alone. The cooling climate created new types of environmental stress that selected for enhanced physiological flexibility. Animals evolved better mechanisms for dealing with temperature fluctuations, variable food availability, and changing water chemistry. These adaptations often involved trade-offs, where enhanced tolerance for one type of stress came at the cost of performance under other conditions. Symbiotic relationships became more common and more sophisticated during the transition period. As environmental conditions became more challenging, species found advantages in forming partnerships that allowed them to exploit resources or tolerate conditions that neither could handle alone. These relationships ranged from simple mutualisms to highly integrated partnerships that blurred the boundaries between different organisms. The geographic patterns of biodiversity that we see in the modern world began to take shape during this transition period. Tropical regions, which remained warm and stable, became centers of evolutionary innovation and species accumulation. Polar regions, experiencing the most dramatic cooling, became dominated by species adapted to seasonal extremes and variable conditions. The evolutionary innovations that emerged during this transition from greenhouse to more moderate conditions created the biological toolkit that life would use to survive all future environmental changes. The flexibility, intelligence, and physiological sophistication that evolved during this period became the foundation for the remarkable diversity of life forms that would eventually populate every corner of our planet. As the cooling continued and climate patterns became more familiar, these evolutionary innovations would be tested by new challenges. Ice ages would come and go, continents would continue their slow dance across the globe, and new environmental pressures would emerge to shape the continuing story of life on Earth. But the fundamental adaptations forged during the recovery from that ancient greenhouse fever would prove their worth time and again, demonstrating the remarkable capacity of life to not just survive change, but to transform it into opportunity. The transition wasn't over yet, though. As atmospheric chemistry continued to shift and climate patterns stabilized into more recognizable forms, one final chapter of this remarkable transformation was about to unfold. The same processes that had cooled the planet from its greenhouse fever were about to create something that hadn't existed on Earth for millions of years. The first hints of ice were beginning to form at the poles, marking the beginning of our planet's journey toward the climate system we know today. The first ice crystals that formed in those high mountain valleys and polar regions weren't dramatic. They appeared quietly, almost apologetically, in places where the angle of sunlight had grown just weak enough, where the atmosphere had thinned just enough, where the slow arithmetic of energy balance had finally tipped toward preservation rather than melting. These weren't the massive ice sheets we associate with ice ages. They were tentative, seasonal, fragile things that might last through a winter and disappear with spring's return. But ice, once it gains a foothold, has a way of encouraging more ice. Those first white patches reflected sunlight that would otherwise warm the ground beneath them. The energy that bounced back into space was energy that couldn't contribute to melting. Slowly, almost imperceptibly, the patches grew larger each winter and retreated less each summer. The planet was learning to be cold again. This wasn't happening everywhere at once. Near the equator, temperatures remained warm enough that the idea of frozen water would have seemed as foreign as ever. The tropics continued to host lush forests and abundant life, creating a world where ice and jungle coexisted on the same planet for the first time in millions of years. The temperature gradient that we take for granted today, the steady cooling from equator to pole, was being re-established after its long absence. The formation of ice at the poles had cascading effects that rippled through every Earth system. Ocean currents that had grown sluggish during the greenhouse period began to strengthen as cold, dense water from polar regions started sinking and flowing toward the equator. This renewed circulation brought oxygen to deep waters that had been stagnant for millennia, restarting the great conveyor belt of oceanic circulation. Marine life responded to these changes with another burst of evolutionary innovation. Species that had adapted to warm, oxygen-poor deep waters suddenly found themselves in environments that were cooling and becoming more oxygenated. Some thrived in the new conditions, while others retreated to the remaining warm water refugia. The ocean was becoming vertically stratified in ways it hadn't been since before the greenhouse period. On land, The strengthening temperature gradients created migration corridors that followed the seasons. Animals began developing behaviors that would become fundamental to life in a climate-zoned world. Seasonal migration wasn't just about following food sources anymore. It was about following temperature zones that moved predictably across the landscape as the planet tilted through its annual cycle around the sun. The atmospheric circulation patterns that had been disrupted by uniform global heating began to reorganize into configurations that would be recognizable to modern meteorologists. Trade winds re-established their patterns as temperature differences between different latitudes provided the energy to drive air movement. The jet streams that guide weather systems across continents began to form as thermal contrasts strengthened at middle latitudes. Weather itself became more varied and interesting as these circulation patterns stabilized. Instead of the relatively monotonous heat and humidity that had characterized the greenhouse period, different regions began experiencing distinct seasonal patterns. Some areas developed wet and dry seasons. Others experienced temperature cycles that ranged from warm summers to genuinely cool winters. The planet was rediscovering seasonal rhythm. Plant communities responded to this increasing seasonality with adaptations that would define terrestrial ecosystems for millions of years to come. Deciduous behavior evolved as trees learned to shed their leaves during unfavorable seasons, conserving energy and resources until growing conditions improved. Seed dormancy mechanisms developed, allowing plants to time their reproduction to coincide with optimal conditions for offspring survival. The cognitive demands of surviving in seasonally variable environments drove continued brain evolution in many animal lineages. Memory systems became even more sophisticated as creatures needed to remember not just where resources were located, but when they would be available. Internal biological clocks evolved to help animals anticipate seasonal changes and prepare for them in advance. Hibernation and estivation behaviors emerged as some animals learned to enter states of reduced metabolism during periods when environmental conditions were too harsh for active life. These weren't simple responses to immediate conditions, but rather anticipatory behaviors that required complex physiological and behavioral adaptations. Animals had to learn to read environmental cues that predicted coming seasonal changes. The storage of energy and resources became crucial survival strategies as environments became less predictable. Fat storage systems became more efficient, allowing animals to build reserves during abundant periods that could sustain them through lean times. Some species developed cached behaviors, hiding food resources that could be retrieved when needed. Others evolved social systems that allowed for resource sharing within groups. Migration patterns became more sophisticated and long-distance as climate zones became more distinct and separated by greater distances. Animals developed remarkable navigation abilities, using everything from magnetic fields to star patterns to maintain course during journeys that might span thousands of kilometers. The timing of these migrations became precisely calibrated to seasonal cycles and resource availability. Bird evolution accelerated dramatically as flying creatures found numerous advantages in the increasingly zoned climate system. Different species specialized for different types of flight, from the long-distance soaring needed for seasonal migration to the precise maneuvering required for hunting in specific habitat types. Feather evolution became more sophisticated, with different plumage adaptations for insulation, display, and aerodynamic efficiency. Mammalian fur evolved greater complexity as animals adapted to wider temperature ranges and more variable conditions. Some species developed seasonal coat changes, growing thicker fur for winter and shedding it for summer. Others evolved specialized fur types for specific environmental conditions, from the water-repelling coats of semi-aquatic species to the insulating properties needed for high-altitude living. The formation of distinct climate zones created opportunities for evolutionary specialization that hadn't existed during the uniform greenhouse period. Arctic adaptations began appearing in species that colonized the newly cold polar regions. Desert adaptations evolved as some areas became more arid due to changing precipitation patterns. Mountain adaptations developed as elevation gradients created vertical climate zones. Ocean chemistry continued its gradual rebalancing as circulation patterns strengthened and atmospheric carbon dioxide levels stabilized at lower concentrations. The acidification that had characterized greenhouse seas slowly gave way to more neutral pH levels. Shell-building organisms that had survived in refugia began to expand their ranges again, creating more complex marine food webs. Coral reef systems experienced a renaissance as water temperatures moderated and chemistry improved. The reef-building organisms that emerged from this period were more resilient and diverse than their predecessors, having been selected for their to-survive environmental stress. These recovery reefs became centers of marine evolution, supporting incredible diversity in relatively small areas. The deep ocean, no longer oxygen-starved, became habitable for complex life forms that had been excluded during the greenhouse period. New communities of deep-sea organisms evolved, exploiting the organic matter that rained down from productive surface waters. Entire ecosystems developed around deep-sea features like hydrothermal vents and cold seeps. Seasonal upwelling patterns became more predictable as ocean circulation stabilized, creating marine oases of productivity that occurred at regular times and places. Marine life evolved to exploit these predictable bursts of nutrients, with some species timing their reproduction to coincide with upwelling events that would provide abundant food for their offspring. The strengthening of ocean currents created marine highways that facilitated long-distance dispersal of many species. Some organisms evolved to exploit these currents for transportation, developing life stages specifically adapted for long-distance travel in flowing water. This enhanced connectivity contributed to continued evolutionary innovation as genes flowed between distant populations. Coastal environments became more dynamic as tidal ranges increased and wave action strengthened due to improved circulation patterns. Rocky intertidal zones developed complex communities adapted to regular cycles of exposure and submersion. Sandy beaches became migration corridors for species moving between marine and terrestrial environments. The chemistry of precipitation changed as atmospheric circulation patterns evolved. Different regions began receiving rainfall with distinct chemical signatures that reflected the oceanic and atmospheric processes that generated them. Plants evolved to exploit these chemical differences, with some species becoming specialized for particular types of precipitation chemistry. Soil development accelerated in many regions as temperature and moisture cycles became more pronounced. Freeze-thaw cycles in newly cold regions created physical weathering that broke down rock into soil particles. Wet-dry cycles in seasonal climates promoted chemical weathering that released nutrients essential for plant growth. The diversity of soil types increased dramatically as different climate zones developed distinct weathering patterns. River systems adjusted to new precipitation patterns and seasonal cycles. Some rivers that had flowed continuously during the greenhouse period became seasonal, flowing strongly during wet periods and nearly disappearing during dry seasons. Aquatic life adapted to these variable conditions, with some species evolving the ability to survive in temporary pools or migrate to permanent water sources. Lake ecosystems became more stratified, as seasonal temperature cycles created thermal layers that mixed and separated on annual cycles. This stratification created distinct habitats within single bodies of water, promoting evolutionary diversification as different species adapted to surface waters, deep waters, and the interfaces between them. Wetland environments expanded in some regions and contracted in others as precipitation patterns reorganized. These transitional ecosystems became crucial evolutionary laboratories where aquatic and terrestrial species continued to exchange genetic innovations. Many of the physiological adaptations that allow modern organisms to survive in variable environments first evolved in these dynamic wetland systems. The atmospheric chemistry itself became more dynamic as seasonal cycles of plant growth and decay created annual fluctuations in gas concentrations. Oxygen levels varied with photosynthetic activity. Carbon dioxide concentrations fluctuated with seasonal patterns of plant growth and dormancy. These cyclical changes created new selective pressures that influenced the evolution of respiratory and metabolic systems. Weather prediction became a valuable survival skill as climate patterns became both more variable and more predictable within their variability. Animals that could sense approaching storms, seasonal changes, or longer-term climate shifts gained significant advantages over those that could only react to immediate conditions. Sensory systems evolved greater sensitivity to atmospheric pressure, humidity, and electromagnetic changes that preceded weather events. The transition from greenhouse to climate-zoned world represented one of the most significant reorganizations of Earth's systems in hundreds of millions of years. The planet was essentially learning how to be a different kind of world, one where energy gradients drove circulation, where seasons created temporal niches, and where environmental diversity promoted biological innovation. This wasn't the end of Earth's climate story, but rather the beginning of the modern climate system that would shape all subsequent evolution. The ice that was forming at the poles would eventually grow into massive sheets that would advance and retreat in cycles, creating the ice ages that would define the most recent chapters of Earth's history. But the foundation for this more familiar world was being laid during this transition period. The species that survived and thrived during this transformation carried with them genetic and behavioral innovations that had been tested by some of the most extreme environmental changes in Earth's history. They had learned to be flexible, adaptable, and resilient. These qualities would serve them well as the planet continued its journey toward the modern climate system, with all its variability, seasonality, and regional diversity. The recovery from that ancient 5-degree warming wasn't just a return to cooler conditions. It was the birth of a new kind of Earth, one that had learned from its fever and emerged more complex, more varied, and more capable of supporting the incredible diversity of life that would eventually include creatures capable of studying their own planet's history. The same processes that had once threatened to overwhelm Earth's systems had ultimately made them stronger, more resilient, and more interesting. And deep within the ice that was beginning to accumulate at the poles, the memory of that ancient warming was being preserved, locked away in frozen bubbles of ancient atmosphere that would one day tell future scientists the story of how their world had learned to balance fire and ice, abundance and scarcity, stability and change. The fever had broken, but its lessons remained, written in the chemistry of ice and stone, waiting to be discovered by minds that evolution itself had shaped during that remarkable transformation. As those first patches of ice took hold at the poles, something profound was happening beneath the surface of the world's oceans. The same cooling that was creating those tentative white expanses was fundamentally altering the chemistry of seawater in ways that would echo through millions of years of evolution. The oceans during the greenhouse period had been like vast, warm bathtubs, stratified into layers that barely mixed. The surface waters, heated by the intense greenhouse atmosphere, had formed a cap over deeper waters that grew increasingly stagnant and oxygen poor. But as temperatures began their slow decline and polar ice started forming, this aquatic stillness was about to be shattered by one of the most powerful forces on our planet: density-driven circulation. Cold water is heavier than warm water. It's a simple physical principle that would reshape the entire marine realm. As polar regions cooled enough for ice to form, the surrounding seawater began to chill as well. This cold, dense water started sinking, creating the first deep water currents the planet had seen in millions of years. Like a sleeping giant awakening, the ocean began to breathe again. The effects were immediate and dramatic. Deep waters that had been oxygen-starved for millennia suddenly found themselves refreshed by cold, oxygen-rich water descending from the surface. Entire communities of deep-sea organisms that had been eking out existence in low oxygen conditions suddenly found themselves in environments that could support much more active lifestyles. This wasn't just about oxygen, though that was crucial. The renewed circulation brought nutrients from the deep ocean to the surface, creating upwelling zones where cold, nutrient-rich water rose to meet sunlight. These areas became marine oases, explosions of productivity that supported food webs of incredible complexity and abundance. Imagine standing on a cliff, overlooking one of these ancient upwelling zones. The water would have been a different colour entirely from what we see in modern oceans, thick with plankton and marine life. Schools of fish so vast they darkened. The water moved through seas that teemed with creatures we can barely reconstruct from fossil fragments. The ocean was coming alive in ways it hadn't for millions of years. Marine predators evolved rapidly to exploit this new abundance. Early whales, already committed to aquatic life, found themselves in seas that could support much larger body sizes than had been possible during the nutrient-poor greenhouse period. The path toward becoming the largest creatures ever to live on Earth was being paved by these newly productive seas. But the changes weren't just biological. The chemistry of the ocean itself was transforming as circulation patterns strengthened. Carbon dioxide that had been trapped in stagnant deep waters began to be mixed back to the surface, where it could exchange with the atmosphere. This oceanic ventilation helped regulate atmospheric chemistry, creating feedback loops that would influence climate stability for millions of years to come. The formation of distinct temperature zones in the ocean created new types of marine environments that hadn't existed during the uniform warmth of the greenhouse period. Tropical seas remained warm and supported different communities than the newly cooled polar waters. Temperate zones emerged as transition areas with their own unique characteristics. Coral reef systems, having survived the acidic waters of the greenhouse period in small refugia, began one of the most remarkable comeback stories in the history of life. But the reefs that emerged from this recovery were fundamentally different from their predecessors. They were built by organisms that had been tested by extreme conditions and had evolved greater resilience and flexibility. These recovery reefs weren't just returning to previous forms. They were experimenting with new architectural styles, new symbiotic relationships, and new ways of building calcium carbonate structures that could withstand environmental stress. The diversity of reef-building organisms exploded as different species tried different strategies for thriving in the improving but still variable ocean chemistry. The strengthening ocean currents created marine highways that connected distant parts of the globe in ways that hadn't been possible during the sluggish circulation of the greenhouse seas. Marine organisms began epic migrations, following currents that could carry them thousands of kilometers across ocean basins. Genetic exchange between distant populations increased, accelerating evolutionary innovation. Some of the most remarkable adaptations emerged in the boundary zones between different water masses. Where warm tropical waters met cooler temperate currents, or where surface waters mixed with deep upwelling, unique communities evolved to exploit the chemical and temperature gradients. These transition zones became evolutionary laboratories where species experimented with physiological flexibility. The seasonal patterns that were emerging on land were mirrored by seasonal changes in ocean circulation. Currents that flowed strongly during certain times of year created predictable patterns of nutrient availability and temperature variation. Marine life evolved to exploit these rhythms, timing reproduction and migration to coincide with favorable oceanic conditions. Deep sea environments, transformed by the return of oxygenated water, became habitable for complex life forms that had been excluded for millions of years. Entire ecosystems developed around features like underwater mountain ranges and volcanic vents. The deep ocean, once a biological desert, became a frontier for evolutionary exploration. The chemistry of marine sediments changed dramatically as circulation patterns evolved. Organic matter that had accumulated in oxygen-poor deep waters during the greenhouse period was suddenly exposed to oxygenated conditions. Some of this material was recycled back into marine food webs, while other portions were buried and preserved, eventually forming some of the oil and gas deposits that would be discovered millions of years later. Coastal environments became more dynamic as wave action increased due to strengthened circulation patterns. Rocky shorelines that had been relatively during the greenhouse period, suddenly calm, experienced powerful wave action that created complex intertidal zones. These areas became crucibles of evolution, where organisms had to adapt to regular cycles of submersion and exposure. The formation of distinct oceanic climate zones created opportunities for evolutionary specialization that paralleled what was happening on land. Arctic marine adaptations began appearing in species that colonized the newly cold polar waters. Deep water adaptations evolved as the abyss became habitable again. Tropical specializations continued to develop in equatorial regions. Marine food webs became more complex and interconnected as productivity increased, and circulation patterns created predictable connections between different oceanic regions. Energy could flow more efficiently through marine ecosystems, supporting larger predators and more intricate ecological relationships than had been possible during the greenhouse period. The acoustic environments changed as well of the OC. Sound travels differently through water of varying temperature and density. As thermal layers became more distinct, marine animals had to adapt their communication strategies. Some species evolved more sophisticated echolocation abilities, while others developed new ways to send acoustic signals across the complex sound channels created by temperature gradients. Chemical communication in marine environments became more nuanced as water chemistry stabilized and circulation patterns created predictable dispersal routes for waterborne signals. Some species evolved the ability to release pheromones that could travel along current systems to reach distant members of their population. Others developed chemical recognition systems that allowed them to identify water thermal regulation prevents favorable conditions. The heat from recovery of oceans' renewed masses with extended far beyond marine ecosystems. Oceanic circulation had global implications that the atmosphere's ability to transport stabilize global temperature patterns. This to active had been solely have occurred if distribution. Atmospheric chemistry was equatorial to polar regions help responsible for heat the extreme temperature swings that might influence by the ocean's return circulation. Gases dissolved in deep waters were brought organisms. The formation of sea-stable conditions for terrest, well as marine oceanic ventilation, helped regulate atmospheric composition back to the surface where millions of years. Ice associate, creating moored ecosystems developed. With specialized entirely new types, ice at the poles created the interfacial life as of marine habitat. They could exchange with the atmosphere. This that hadn't existed for organisms adapted to life between frozen and liquid water. These polar of the most productive marine communities would eventually become some ecosystems on the planet. Seasonal sea ice formation and melting created annual pulses of fresh water input that affected coastal circulation patterns. Marine organisms evolved to exploit these seasonal changes, with some species timing their reproduction to coincide with ice melt events that brought nutrients and changed local water chemistry. The gradual cooling of polar waters created temperature gradients that drove also smaller scale mixing, not just large-scale circulation, but processes. Eddies, upwelling cells, and other mesoscale features became more common and more predictable, creating a complex mosaic of marine microenvironments that supported incredible diversity. Tidal patterns became more pronounced as ocean circulation strengthened and coastal geography evolved. The interaction between tides, currents, and coastal topography created complex hydrodynamic environments that challenged marine life in new ways, while also creating new opportunities for evolutionary innovation. The transition from greenhouse oceans to the more familiar circulation patterns we see today represents one of the most significant reorganizations of marine systems in Earth's history. It wasn't just a return to previous conditions, but rather the emergence of a new kind of ocean one that had learned from its stagnant period and evolved more robust and dynamic circulation patterns. Marine life that survived this transition carried with them adaptations that had been tested by some of the most extreme oceanic conditions in Earth's history. They had learned to survive in low-oxygen environments, to tolerate acidic water chemistry, and to exploit variable and unpredictable conditions. These adaptations would serve them well as oceanic conditions continued to evolve. The renewed circulation also created the physical framework for all future oceanic evolution. The current systems that emerged during this period would continue to influence marine life for millions of years, creating the dispersal routes, mixing zones, and productivity centers that would shape the evolution of everything from microscopic plankton to the largest whale circulation patterns, stabile. As the ocean currents strengthened and globalized, they were setting the stage for the next chapter in Earth's climate story. The ice that was forming at the poles would eventually grow into massive sheets, but the oceanic circulation system that was emerging would be crucial for transporting the heat and moisture that would determine where those ice sheets could grow and how they would behave. The recovery of oceanic circulation from the stagnant greenhouse period demonstrates one of Earth's most remarkable characteristics: its ability to reorganize its own systems in response to changing conditions. The ocean didn't just passively respond to cooling temperatures, it actively participated in creating the new climate system that was emerging. This oceanic renaissance was laying the foundation for the modern marine realm, with all its complexity, productivity, and diversity. The same circulation patterns that were emerging from the greenhouse recovery would eventually support the incredible abundance of marine life that would populate Earth's oceans for millions of years to come. And as the currents grew stronger and the temperature gradients sharpened, they were creating the conditions that would allow life to make one of its most audacious evolutionary leaps. In the cooling seas, where circulation was bringing new opportunities and new challenges, some of the most remarkable creatures in Earth's history were about to make their appearance. Animals so large and so sophisticated that they would redefine what was possible for life in the ocean. The creatures that would emerge from these newly energized seas were unlike anything that had ever existed before. In the nutrient-rich waters where ancient currents were learning to flow again, evolution was about to attempt something that seemed almost impossible. It was going to take mammals, creatures that had evolved for life on land, and transform them into the largest animals that would ever grace our planet. The early ancestors of whales were still recognizable as land mammals when this oceanic revolution began. They had 4 legs, fur, and the basic body plan of terrestrial creatures. But the abundant food sources in these recovering seas created opportunities that land could never provide. Schools of fish moved through waters so thick with nutrients that they supported biomasses unimaginable in terrestrial environments. These proto-whales began spending more time in coastal waters, following food sources that were becoming increasingly aquatic. Each generation ventured a little deeper, stayed submerged a little longer, and became slightly better adapted to life in the water. Their limbs began to change shape, elongating and flattening to become more efficient for swimming. Their nostrils started migrating toward the tops of their heads, making breathing easier while partially submerged. But the truly remarkable transformation was happening inside their bodies. The renewed oceanic circulation was creating acoustic environments unlike anything that had existed during the stagnant greenhouse seas. Sound waves could travel vast distances through water masses of different temperatures and densities. Some whale ancestors began exploiting these acoustic highways, developing the ability to produce and interpret sounds that could carry across entire ocean basins. The evolution of echolocation in early whales represents one of the most sophisticated sensory adaptations in the history of life. These creatures learned to see with sound, creating detailed mental maps of their environment by interpreting the echoes of their own vocalizations. In the dark depths where sunlight couldn't penetrate, they developed a form of perception that was arguably more detailed and precise than vision itself. The social implications of these acoustic abilities were profound. Whales could maintain contact with family members across distances that would be impossible for terrestrial animals to span. They developed complex communication systems that allowed for coordination of group behaviors over scales measured in hundreds of kilometers. The ocean became a medium for social connection in ways that land environments simply couldn't support. As these marine mammals grew larger, they faced new physiological challenges that pushed evolution in unexpected directions. Diving to depth required adaptations for managing pressure that land animals had never needed. Their blood chemistry changed to store more oxygen. Their lungs developed the ability to collapse safely under pressure. Their bones became denser to help with buoyancy control. The cardiovascular systems of early whales underwent remarkable transformations. Hearts grew larger and more efficient to pump blood through bodies that were becoming truly massive. Specialized blood vessel arrangements evolved to help maintain circulation during long dives. Countercurrent heat exchange systems developed to prevent heat loss in cold water while maintaining the high metabolic rates needed to support such large, active bodies. Brain evolution in whale lineages accelerated dramatically during this period. The cognitive demands of navigating three-dimensional aquatic environments, processing complex acoustic information, and maintaining sophisticated social relationships drove the development of some of the largest and most complex brains in the animal kingdom. Whale intelligence began to rival and in some ways exceed that of their terrestrial counterparts. The feeding strategies that evolved among early whales were as diverse as they were ingenious. Some species developed baleen, fibrous plates that could filter enormous quantities of small organisms from the water. Others evolved powerful teeth and sophisticated hunting techniques for capturing large prey. The abundance of food in the recovering oceans supported both strategies and allowed for incredible specialization. Migration patterns emerged that took advantage of the strengthening ocean currents and seasonal productivity cycles. Some whale species began undertaking journeys that spanned entire ocean basins, following food sources and breeding opportunities across thousands of kilometers of open water. These migrations required navigation abilities that rivaled those of any creature on land or in the air. The reproductive strategies of whales also adapted to aquatic life in remarkable ways. Mating behaviors evolved that took advantage of the three-dimensional nature of the marine environment. Some species developed complex courtship rituals that involve synchronized swimming, acoustic displays, and physical demonstrations of size and strength. The care of offspring in aquatic environments required innovations in nursing, protection, and teaching that had no precedent in terrestrial mammals. The diversity of whale species that emerged during this period was extraordinary. Giants that fed on the smallest organisms shared the seas with smaller, more agile predators that hunted fish and squid. Some species developed highly specialized feeding techniques, while others remained generalists, capable of exploiting a wide variety of food sources. The recovering oceans provided enough ecological niches to support this incredible diversity. The relationship between whales and their environment became one of the most intimate connections between organism and ecosystem in the natural world. Whales didn't just live in the ocean, they became part of its circulation patterns. Their migrations helped transport nutrients between different oceanic regions. Their feeding activities influenced plankton distributions. Their waste products fertilized marine ecosystems across vast areas. The acoustic landscape of the oceans was transformed by the presence of these vocal giants. Whale songs could travel across entire ocean basins, creating a planetary communication network that operated on scales never before achieved by any biological system. Different species developed distinct vocal signatures, creating acoustic communities that spanned continents. The evolution of whale intelligence during this period included the development of cultural transmission, the ability to pass learned behaviors from one generation to the next through teaching rather than genetic inheritance. Different whale populations began developing distinct behavioral traditions, tool use patterns, and social customs that were passed down through generations like primitive cultures. The physiological extremes achieved by whale evolution pushed the boundaries of what was thought possible for mammalian life. Some species developed the ability to hold their breath for over an hour while diving to depths where pressure would crush most other organisms. Others evolved the capacity to generate sounds loud enough to be heard across entire ocean basins, while maintaining the acoustic sensitivity needed to detect the faintest echoes. The social structures that developed among whale species became some of the most complex in the animal kingdom. Multi-generational family groups maintained relationships across decades. Cooperative hunting strategies emerged that required sophisticated coordination and communication. Some species developed what can only be described as whale cultures, with distinct regional variations in behavior, communication, and social organization. The sensory worlds of whales expanded beyond anything experienced by terrestrial mammals. In addition to their remarkable acoustic abilities, some species developed enhanced magnetic sensitivity for navigation, sophisticated chemical detection systems for tracking prey across vast distances, and pressure sensitivity that allowed them to detect water movements from hundreds of kilometers away. The metabolic innovations required to support such large active bodies in aquatic environments drove the evolution of some of the most efficient energy utilization systems in the natural world. Whales learned to extract maximum energy from their food sources while minimizing the energy costs of swimming, diving, and maintaining their massive bodies in cold water. The reproductive success of whales during this period of oceanic recovery was remarkable. The abundant food sources and improved environmental conditions allowed for rapid population growth and expansion into new oceanic territories. Whale diversity reached levels that wouldn't be seen again until modern times, with dozens of species filling every available marine niche. The co-evolution between whales and their prey species created some of the most dynamic predator-prey relationships in the natural world. Fish and squid populations evolved new escape strategies, camouflage techniques, and schooling behaviors in response to whale predation. This evolutionary arms race drove innovation on both sides, contributing to the overall diversification of marine life. The impact of whale evolution on global oceanic systems was profound. These massive creatures became integral components of oceanic nutrient cycles, carbon transport systems, and even climate regulation. Their presence in such large numbers helped shape the very chemistry and circulation patterns of the seas they inhabited. The story of whale evolution during the oceanic recovery represents one of the most successful adaptive radiations in the history of life. In the span of just a few million years, these remarkable creatures transformed from small, terrestrial mammals into the largest animals ever to exist on Earth. Their success demonstrated the incredible opportunities that became available as oceanic circulation systems recovered from the greenhouse period. As whales continued to diversify and spread throughout the world's oceans, they were inadvertently setting the stage for one of the most important ecological relationships in marine systems. Their feeding activities, migration patterns, and waste production were creating the conditions that would support some of the most productive marine ecosystems ever to exist. The acoustic abilities of whales also began to influence the evolution of other marine creatures. Fish, squid, and even some invertebrates developed enhanced hearing abilities in response to the whale-dominated acoustic environment. Some species learned to exploit whale communication signals for their own navigation and feeding purposes, creating complex acoustic webs that connected different levels of marine food chains. The success of whale evolution during this period provides a remarkable example of how environmental recovery can create opportunities for biological innovation on an unprecedented scale. The same oceanic changes that were restoring circulation patterns and productivity were also enabling the evolution of some of the most magnificent creatures ever to inhabit our planet. And as these giants of the sea continued to evolve and diversify, the ice that had begun forming at the poles was slowly but steadily expanding its reach. The same cooling that had enabled oceanic recovery was now beginning to create the next chapter in Earth's climate story, one that would test the adaptability of all life forms, including these newly evolved marine giants. The interplay between biological evolution and environmental change during this period demonstrates one of the most fundamental principles of life on Earth. Change creates opportunity, but only for those organisms flexible enough to exploit it. The whales that emerged from the oceanic recovery carried with them the genetic and behavioral innovations that would allow them to survive whatever environmental changes lay ahead. Their story reminds us that even the most extreme environmental transformations can become catalysts for evolutionary breakthroughs. The same oceanic stagnation that had threatened marine life during the greenhouse period ultimately created the conditions that would give rise to some of the most remarkable creatures in Earth's history. Life doesn't just survive change, it transforms change into opportunity, creating new forms of beauty and complexity that enrich the biosphere for millions of years to come. The ice sheets that slowly began creeping outward from those polar mountain valleys carried with them the memory of everything that had come before. Each layer that accumulated told a story, not just of temperature and precipitation, but of the very air that ancient creatures had breathed. Trapped within those frozen layers were tiny bubbles of atmosphere from the greenhouse world, preserved like time capsules waiting to be discovered millions of years in the future. As the ice expanded, it began to exert its own influence on the planet's systems. The white surface reflected sunlight back into space with an efficiency that dark could never match. This ocean or forest is a positive feedback loop, where albedo effect creates cooling, enabling more ice formation, which causes more cooling, enabling even more ice. The planet was to be cold again, teaching itself how, one frozen crystal at a time. The weight of accumulating ice began to depress the land beneath it, creating basins that would eventually become the Great Lakes and countless other water bodies. The ice wasn't just sitting on top of the landscape, it was actively sculpting it, carving valleys, grinding down mountains, and redistributing enormous quantities of rock and sediment across continents. Animals living at the margins of these expanding ice sheets faced evolutionary pressures unlike anything their ancestors had experienced during the greenhouse period. The climate zones that had been stable for millions of years were now shifting, compressing, and reorganizing on timescales that challenged adaptation. Some species followed their preferred temperatures as they migrated toward the equator, while others learned to tolerate conditions their lineages had never before encountered. The seasonal patterns that had emerged during the early cooling now became more extreme as ice sheets grew larger and more permanent. Winters grew longer and harsher in regions adjacent to the ice. Summers became brief interludes of warmth that had to support all the biological activity that would sustain life through months of cold and darkness. Plants evolved new strategies for cramming entire life cycles into these compressed growing seasons. Migration became not just advantageous, but essential for many species. The predictable seasonal movements that had begun during the greenhouse recovery now became epic journeys spanning continents. Birds developed navigation systems of extraordinary sophistication, using magnetic fields, star patterns, and landscape features to guide them along routes that might cover thousands of kilometers twice each year. Hibernation evolved in numerous mammalian lineages as a strategy for surviving extended periods when food was scarce and temperatures were hostile. This wasn't simply sleeping through the winter, but rather a complex physiological transformation that allowed animals to reduce their metabolic rates to tiny fractions of normal levels, while maintaining just enough biological activity to stay alive until spring returned. The cognitive demands of surviving in this increasingly seasonal world drove continued brain evolution in many species. Memory systems became even more sophisticated as animals needed to remember not just where resources were located, but when they would be available across multi-year cycles. Some species developed the ability to track seasonal patterns across decades, remembering which years brought early springs or harsh winters. Social behaviors evolved to help groups of animals survive the challenges of seasonal scarcity. Cooperative food storage became common, with some species developing elaborate caching systems that could sustain entire communities through lean periods. Others evolved social hierarchies that determined access to resources during times of shortage, ensuring that at least some individuals would survive to reproduce when conditions improved. The forests that had once stretched unbroken from pole to pole began to fragment into distinct biomes, separated by climate barriers. Temperate forests developed in middle latitudes, characterized by deciduous trees that shed their leaves each autumn in preparation for winter. Boreal forests emerged at higher latitudes, dominated by evergreen conifers that could photosynthesize whenever temperatures allowed. Even during brief winter warm spells, grasslands expanded in regions where the climate became too dry or too cold to support forests. These open habitats created new opportunities for grazing animals and their predators. The mammals that adapted to grassland life developed longer legs for running across open terrain, more efficient digestive systems for processing tough grasses, and enhanced sensory capabilities for detecting predators in environments with limited cover. Arctic tundra appeared for the first time in millions of years as the ice sheets created zones of permanently frozen ground. This harsh environment supported only specially adapted plants that could complete their life cycles during the brief summer growing season. Animals that colonized the tundra evolved extreme cold tolerance, thick insulation, and behavioral adaptations for finding food in landscapes that were barren for much of the year. Desert environments expanded in some regions as changing precipitation patterns created areas of permanent aridity. The plants and animals that adapted to desert life developed remarkable water conservation abilities, heat tolerance mechanisms, and behavioral strategies for surviving in environments where resources were scarce and conditions were extreme. High-altitude environments became more distinct as mountain glaciers expanded and temperature gradients became steeper with elevation. Alpine plants evolved compact growth forms, enhanced UV protection, and accelerated life cycles that could take advantage of brief growing seasons. Mountain animals developed enhanced oxygen utilization systems and specialized appendages for moving across steep, rocky terrain. The ocean currents that had strengthened during the early recovery now became the primary mechanism for transporting heat around the planet. The thermohaline circulation, driven by differences in water temperature and salinity, created a global conveyor belt that moderated what would otherwise have been even more extreme temperature differences between equator and poles. Marine ecosystems reorganized around these new circulation patterns. Upwelling zones became more predictable and productive, supporting massive populations of fish and marine mammals. Deep water formation in polar regions created oxygen-rich environments that could support complex communities of organisms that had been excluded from the stagnant seas of the greenhouse period. The ice sheets themselves became habitat for entirely new types of organisms. Polar bears evolved from terrestrial ancestors, developing the ability to hunt seals through breathing holes in sea ice. Arctic foxes, snowy owls, and countless other species adapted to life in environments where ice and snow were permanent features rather than seasonal inconveniences. Seasonal sea ice formation and melting created dynamic marine environments that pulsed with biological activity. Algae that grew on the underside of ice created food webs that supported fish, seals, whales, and seabirds. The timing of ice breakup became crucial for species that depended on these ice-associated ecosystems, with reproduction and migration patterns synchronized to the rhythms of freezing and thawing. The chemical composition of the atmosphere continued to evolve as ice sheets grew larger and more permanent. Water vapor levels decreased as more of the planet's water became locked in frozen form. This reduced one of the important greenhouse gases, creating a feedback loop that reinforced cooling. the planet was actively participating in its own refrigeration. Volcanic activity during this period took on new significance as the ash and gases released by eruptions could now trigger more dramatic climate responses. A major volcanic event could initiate cooling that would persist for years, potentially triggering the formation of new ice sheets or the expansion of existing ones. The planet's climate system was becoming more sensitive to perturbations, both warming and cooling. Plant communities adapted to the increasingly variable climate developed greater resilience and flexibility. Many species evolved the ability to remain dormant for extended periods, waiting out unfavorable conditions that might last for years rather than seasons. Seed banks became more sophisticated, with some plants producing seeds that could remain viable for decades before germinating when conditions improved. The pollinating relationships between plants and insects became more precisely timed as seasonal windows for reproduction became narrower and more critical. Some plant species evolved to bloom in synchrony with the emergence of their specific pollinators, creating intricate ecological partnerships that required precise coordination between different organisms' life cycles. So there you have it, the extraordinary tale of what happened the last time Earth heated by just 5 degrees. From those tropical forests at the poles to the massive marine giants that emerged from recovering seas, we've witnessed how our planet can transform itself in ways that seem almost impossible until they actually happen. The mammals that survived that ancient fever carried with them innovations forged in the crucible of change, adaptations that would define life on Earth for millions of years to come. As we face our own climate transformation today, perhaps the most remarkable lesson from that distant greenhouse world isn't about the dangers of change, but about life's incredible capacity to turn upheaval into opportunity, creating new forms of beauty and resilience that endure long after the fever breaks.